In the previous videos, we introduced binary search tree. We talked about search, insert, delete, floor, and seal operations. We observed that all these operations have the time complexity as big O of h. So if height of your binary search tree is n, then all these operations become linear, and if height is log n, then they all become logarithmic. The idea of self-balancing binary search tree is to keep the height in check, is to make sure that height never goes beyond theta log n. If we keep the height as theta log n, then all these operations become theta log n. Now, how is height of BST decided? It depends upon how are you inserting the keys. Same set of keys in a BST can generate different heights. For example, I have some keys here, these 7 keys. If I insert these keys in increasing order, I insert 7 first, then 10, then 11, then 15, 30, 35, and then 40. I get a tree like this. But if I insert these keys in this order, 15, 10, 7, 15 comes first, then 10 goes to the left, 7 goes to left, left, 11, left, right, 35, right, 30, right, left, 40, right, right. If I insert this way, I get a perfectly balanced binary search tree. The height of this BST is n, the height of this BST is log n. We just saw that order of insertion decides the height. So if I know all the keys in advance that I'm going to insert in BST, I can make an order which will always give me perfectly balanced binary search tree. For example, if I know that I am going to insert these keys in my BST, I'll consider these keys in the sorted order. I'll take the mid key and make it root. Right? And now I know half of the keys are going to be the left subtree and half of the keys are going to the right subtree. Then I'll recursively build the left subtree using the same logic. Pick the mid and make it root of left subtree. Then 7, then 11. For right subtree, again pick the mid and make it root of the right subtree. Then left and then right. So if I know keys in advance, I have a way to build perfectly balanced binary search tree. I can simply sort the keys, then I can take the middle, make it root, then recursively do the same thing for building the left subtree and recursively do the same thing for building the right subtree. Now the question arises, how to make sure that height of BST remains theta log n when you are randomly inserting items and when you are doing random deletions, because you can't control the way users are going to insert the keys. They can always insert in increasing order. Now, how do you ensure that height of your tree remains theta log n even if the user is inserting in increasing order or decreasing order? Please pause this video and try to think of any way to ensure that height remains theta log n. The main idea of self-balancing binary search tree is to do some extra work when inserting or deleting items. Because insertions and deletions are the operations which can make an already balanced BST unbalanced. So the idea is this: when you are inserting an item, while inserting, if you realize inserting this item is making the BST unbalanced, you do some restructuring in the BST to regain the balance. Same thing with deletion. While deleting an item, if you realize that deleting an item is causing some unbalance, you restructure the BST and make sure that it remains balanced. Let us take a look at this example to get a flavor of restructuring. Say we have an empty BST and we want to insert 100, 200 and 300 into this BST. When we insert 100, nothing goes wrong, it's balanced. When you insert 200, nothing goes wrong, it's balanced. But when you insert 300, it becomes kind of unbalanced. So what restructuring you do is, you bring the 200 at the top, you bring 100 here, and then you bring 300 here. And this restructuring is called rotation. We have mainly left rotated the BST. Left rotation means counterclockwise rotation. Counterclockwise. You brought the 200 at the top, 100 on left side and 300 on the right side. Here is an example of right rotation. Suppose we insert 300, 200 and 100. 300 goes fine, no unbalancing. 200 also goes fine, but when you 100, what happens? It becomes unbalanced. So what do? You rotate this way this time, and this is called right rotation because it's according to the clock direction. So 200 again goes at the top, 100 goes to the left, and 300 goes to the right. The main idea that cell balancing BSTs use is called rotation. Rotation is a great operation. You can restructure the BST without violating the BST property. What is BST property? All the keys in the left side should be smaller and all the keys in the right side should be greater. Without violating this property, we can restructure the BST. And the great thing is, this rotation is a big O one operation. It requires only few changes to references or pointers. Let us see BST rotation in general. We have this BST where P is parent, X can be a left child or right child of P. I've used ... for this reason. Y is a left child of X, and these triangles represent subtrees. They may contain empty subtree or a subtree with one node or two nodes or any number of nodes. So T1 is a subtree of Y, left subtree of Y. This is right subtree of Y. This is right subtree of X. When we do right rotation, we get this tree. Y becomes the root and X becomes the right child of Y. This rotation does not cause any violation in the BST property. Let us see how. In this particular BST, all keys in T1, they have to be smaller than Y. And all keys in T2, they have to be greater than Y. And then X has to be greater than all these. Then T3, all keys in T3, they have to be greater than all these. So this is the order we have in this BST. Let us take a look at this. Do we have the same order here? All keys in T1 are smaller than Y, right? And all keys in T2 are greater than Y because they are on the right side. And all keys in T2, they are smaller than X, and all keys in T3, they are greater than X. So we have the same BST property followed in both BSTs, and we have restructured the BST. That's what the magic of these rotation operations is. Here is an example of right rotation. We have this BST, and before we inserted 5, say this was balanced, right? This was balanced before you inserted 5. You can't get more than this balance, right? Now, when you inserted 5, what happened? This became unbalanced because this side you have too many nodes and this side you have only one node. So how do you balance it? You do this right rotation. You have this as X, this as Y, this is T1, this is T2, and this is T3. And then you do right rotation. You bring this particular 20 at the top. You bring the T1 as left of Y. You bring the T2 as left of X and T3 as right of X. And this is how your BST becomes balanced. Now we'll discuss in detail how do we decide when to do left rotation, when to do right rotation, which nodes to pick for left rotation and right rotation. We'll discuss these operations in detail when we talk about particular cell balancing BSTs. AVL tree and red-black tree are two example cell balancing BSTs. There are more cell balancing BSTs like split tree. Here we are going to focus on these two. AVL tree is very strict in terms of height. It tries to maintain very strict balance. Red-black tree on the other hand is slightly loose in terms of balance. And what is the advantage of red-black tree? Since it is loose in terms of balance, it causes less restructuring when you are doing insert and delete. We will be talking about AVL tree in detail and we will be introducing red-black tree also. In general, red-black tree is used more compared to AVL tree. In Java libraries like tree set and tree map, they use red-black tree. C++ libraries, map and set, they also use red-black tree.